All right, so today we will continue to look at linear regression in matrix notation. We kind of introduced this a little bit on Wednesday, and what I want to do now is I want to expand that so that we can include, higher order terms and things like that. All right, so we left off on Wednesday and we looked at linear regression in matrix notation. And we said, in order for us to find our optimal solution, because the goal is that we've defined an objective function, we said our objective is to find the line or find the set of parameters that will minimize the sum of squared residuals. And those parameters are contained within this vector W. Right now, our parameters are just the intercept and the slope. And depending on the intercept and the slope, our fitted line changes. And depending on how our fitted line changes, our sum of squares residuals will change. And we're looking for the slope and intercept that will minimize the sum of squared residuals. And in order to do that, we want to take the gradient, set it equal to 0, and solve for W. So we take, here's some just useful gradient relationships that if you have some kind of function that outputs a single scalar value and you want to take the gradient of that function with respect to W, these are some of the things that we get. And keep in mind that you can think of the gradient as a vector of partial derivatives of each of the components in W. So therefore, if W itself is a 2x1 matrix, then the gradient of our function f with respect to W is also going to be a 2x1 matrix. And so we left off and we said the loss function, that is, or our objective function where we are saying we have the sum of squared residuals, or the mean squared, not the sum, but the mean squared error, or mean squared residual, is can be found by doing t minus xw transpose times t minus xw, and when you expand that out, you get this thing, t transpose t, w transpose x transpose t, w transpose x transpose xw. And this itself is a single scalar value. That is our loss function that we want to minimize. And what we do is we take the gradient of this with respect to w, we set it equal to 0, and then we solve for w. So doing that, our gradient with respect to w is this, negative 2 x transpose, negative 2 over n x transpose t plus 2 over n x transpose xw. We'll set that equal to 0, and then we solve, and we find that the w that will minimize the mean squared error, or the sum of squared residuals, or whatever we want here, is going to be x transpose x inverse x transpose t. And this is also covered in the class Stats 100C, which some of you have already taken and some of you have not yet taken. But this is also looked at in great detail and great depth there. And this is kind of where we leave off. Okay, or we left off on Wednesday. So what I want to do now is I want to kind of expand this, or actually let's do a couple examples first, okay? So yes, this is going to be the set of parameters, our intercept and our slope, that will minimize this. And so here's a very kind of simple data set. I've got 4 data points, 1, 1, 2, 3, 3, 2, and 4, 4, okay? So my input values are x, the target values are t, or you can also think of it as our y, are this, and we want to fit the line that is going to minimize the sum of squared residuals, or the mean squared error. And so in order to do this, I create my matrix X, which will have a column of 1s, and then my values 1, 2, 3, 4. And then and I'm going to multiply that by the transpose of X. So X transpose X is going to be a 2x2 matrix. And then we want to invert that. Okay, X transpose X inverse is this. And then if I multiply that by X transpose X, so remember the solution is X transpose X inverse times X transpose times T. And therefore, X transpose X inverse times X transpose ends up giving me a 2 by n matrix. In this case, n is 4. I've got 4 data points. And then when I multiply that itself by t, which is n by 1, we get a 2 by 1 matrix. And so this is going to be my intercept, and this will be my slope. So the result is a 2 by 1. This is my W estimates of W hat that minimize the mean squared error to the sum of squared residuals. Okay, 0.5 and 0.8. And so, performing our operations, our matrix operations, X transpose X inverse, X transpose T, gives me an intercept and a slope, intercept of 0.5 and a slope of 0.8. No surprise if I asked R to fit a linear model where I say predict T based on X, R comes back and says, yeah, your intercept is going to be 0.5 and your slope is 0.8. Okay. And so R's LM function, which we can use to estimate linear models, does a different set of operations, but again, it has the same goal of minimizing our sum of squared errors, and so it's no surprise that we get the same results here. If we want, we can predict our values by taking any set of X. So here I'm going to just take my original column or original matrix X and multiply it by W hat, right? So our predicted values are X times W hat. And so we can see these are the values that we are predicting here. So when you input 1, you predict 1.3, 0.5 plus 0.8. And then, when you put in 2, you have 0.5 plus 2 times 0.8. So 0.5 plus 1.6, and you predict 2.1. And this is our fitted line along with our actual values. And so we have a residual between 1.3 and 1. So we have a residual of 0.3 here. Here we have a residual of 0.9, I believe. Yeah, 2.1 is our predicted value. The actual value is 3, so we have a residual of 0.9. Here we also have a residual of 0.9, and here we have a residual of 0.3. And so these are our, predicted values shown in red. The actual values there. The vertical distance between the dot and the line is our residual, and this line minimizes the sum of squared residuals. Okay, so that's that for a toy data set. We could try just something a little bit bigger. And so, we saw this on Wednesday also, and we have our Olympic 100-meter dash gold medal winning race times. And what we see is that, between 1900 or 1896, when the first modern Olympics were held, and up through 2012, which is when the data set ends, we see that overall, running the winning time has gotten faster and faster and faster as the years have gone by. And so we will try to fit a model to this. And so we can start by fitting a linear model, right? And I could just use LM and say predict time based on year. We get this intercept and we get this slope, 36.3, slope of negative 0.013. Okay. We can also do it our matrix notation, and I'll bind a column of ones along with our X values, 1896, 1900, 1904, and so on and so forth. And I can do X transpose X inverse, X transpose T. Okay, and this time my T is that column of Olympic times. And then, no surprise. Again, I get the same intercept and same slope. I get 36.309 as my intercept, which is exactly what LM says. And my slope, negative 0.01328. That's exactly what I have here. Negative 0.13275, but it gets, if you round off, it's exactly the same, negative 0.1328. Okay, and so when we do our matrix operation, we get results that align with what LM says. So that's a good sign. Okay, let me go ahead and give you your first view quiz answer for today, which is the letter A. A as in apple is our first view quiz answer. And similarly, we can do x times our fitted coefficients, x times w hat, to get our predicted values. And what we see is, each year or every kind of 4 years, we see the predicted time drop by around 0.05. Okay. Or I don't know, let's see. No, a little bit less than that, right? Or I don't know. Okay. Drop by something. And so that's what we see here. Okay, so this is the fitted line, as far as the linear regression line goes. Okay. So that's what we have. Now, what if we want to fit a uh, a quadratic term or something like that, okay? If we want a nonlinear response from a linear model, we'll still have a linear model in that it is uh, that, as the x value changes, our prediction goes down by the same amount. Oh, there's a question here. It says, how come we need matrix Olympic time and not just Olympic $ time? This is, I think if you don't include the matrix here, it's going to treat Olympic $time as a row vector rather than a column vector. And then it doesn't work. But maybe it's okay. I don't know. Maybe R is okay enough to just take the vector and do it. By throwing this into a matrix, you'll get, I think you'll get basically an n by one matrix there. And so the dimensions will align there. Whereas the vector technically doesn't have any dimensions. And so maybe R automatically converts it to a matrix. Not 100% sure. Okay, anyway, going back here, let's say we want to expand this, and I'm going to just add a third column. So my X matrix, the previous, we just had the column of ones for the intercept, the column of X's for our slope. And what I'm going to do now is I'm going to add a third column, which is going to be X, our X value squared. Okay, and so this is going to be basically a second order or quadratic term. And this will expand our thing. Now, one of the nice things about working in matrix notation is that all of our predicted values, our x times w, that form, the going all the way back to here, okay, this loss function remains exactly the same. Whether X is a n by 2 matrix or an n by 3 matrix, okay? And whether W is a 2 by 1 or a 3 by 1 matrix, the output is exactly the same. Okay, I'll have an n by 3 and a 3 by 1 instead of an n by 2 and a 2 by 1. And therefore, when I take the gradient with respect to W, when I set it equal to 0, I'm going to get the exact same results. I'm going to get the exact same results when even if I add a third column. Whereas if you took the traditional approach and you did partial derivatives with respect to, each of your terms, W1, W0, W1, and W2, now you have three partial derivatives, three equations, and three unknowns to solve. And, that's a lot more complicated. Okay. So by using matrix notation, despite the initial hurdle in the beginning, it simplifies our work. Okay. And so in order to do this, I will just take my column of x values and I will square it. So just looking at the first few rows, I'll take, I have my column x, which is just the Olympic $ year. And then I'll have x squared. So I'll take, 1896 and I'll square it. And I get 3,594,816 square years. Here we have 1900 and we get what 3,610,000 or something like that. Okay, it's kind of a little bit weird, but again, x is the year, and then we have x squared, and we want to see what can we fit a model here. We will run into an issue a little bit. Yeah, okay. So anyway, here our predictions are, the intercept plus the slope, our first order term, W1 times xn, and W2 times xn squared. And again, our predicted values are still found by doing W transpose xn or x times W for all of our values, right? It's exactly the same. In matrix notation, it's exactly the same as when we had just one variable. And therefore, when we make our predictions for all of our things, it's still just x times w. And this is exactly the same, right? So we have our x matrix, which we've expanded to have 3 columns. Our w vector now has a third term. We have a w0, w1, and w2. But it's still, when you do x times w, you still get exactly the predicted value. And therefore, the loss function remains exactly the same. Because the loss function remains exactly the same in matrix notation, the parameter estimate remains exactly the same. It's still going to be x transpose x inverse x transpose t. And that's kind of the beauty of moving into matrix notation and using linear algebra to solve these problems, is that you don't have to um, deal with 3 separate partial derivatives and solve all of them simultaneously. Or if you have a fourth order term, you don't have, a fourth term, you don't have to have 4 partial derivatives and solve all of them simultaneously. You can just still do the same thing, take the gradient with respect to W, set it equal to 0 and solve, and you get the same results. Okay. So we say, okay, well, let's estimate W hat by doing x transpose x inverse x transpose t. And if we try to do that with our Olympic data, remember, I've expanded my X matrix to have this third column, I run into an error, okay? It says I have X transpose X inverse, the solve there is the inverse part, times X transpose times T, which is the matrix on the Olympic time. And I get this error. It says solve.default system is computationally singular reciprocal condition number equals something, I get an error. And this is a result of dealing of doing mathematical operations on the computer. If we were dealing with real numbers, we would not run into this problem, okay? If we were dealing with real numbers. But the problem is we're doing our mathematical operations, our arithmetic on the computer, which uses floating point numbers, and there are limitations with floating point numbers, okay? So let's just take a look at what's going on. If you look at that matrix, X transpose X, remember we want to get X transpose X inverse. When you take this matrix, X transpose X, look at what happens to this element down here, okay? Remember, our column of X squared, these are really big numbers. 3,610,000, 3,655,000, okay? And so when I do X transpose X, okay, and I'm doing basically 3 million times 3 million, then I'm getting something on the order of 9 times 10 to the 12, okay? And then when you add them all up across all of the, different years, you get something on the order of 4 times 10 to the 14, okay? A really big number. And now we want to invert this, right? We want to find the inverse of this matrix. And so finding the inverse of a 3 by 3 matrix, basically at some point where we are dividing by basically the determinant, okay, which is going to be a really big number, okay, and then um, and basically R detects that we end up with something smaller than machine epsilon, okay? So when we try to invert this, okay, we will run into a problem because basically we're going to be dividing by the determinant at some point. And, we get these really big numbers, 4 million and 4 million squared, we get something on the order of 10 to the 14. And it throws an error, basically telling us that we are hitting the limits of what our computer is able to keep track of. This is not a limitation of just R, it's a limitation of just the floating point number system that we are using, a 64-bit number, which can keep track of a lot of values around 16 decimal places of precision. Okay. But we're dividing by a really big number. And so we run into some of the problems there. Okay. And so the computer says the matrix inverse can't be calculated or doesn't exist. And that's not true. You could, if we had real numbers with infinite decimal precision, we can invert this matrix and we can do X transpose X inverse. It's just the computer itself with the floating point numbers runs into these problems. Okay. And so these are things that we have to keep in mind when we do kind of computational work on the computer, is that we are not dealing with real numbers and we are dealing with basically approximations of real numbers, but that have limitations. Okay. So we can avoid this just by like scaling our numbers down. Okay, there's a question in the chat. It says, do other common programs use the same floating point number system and would therefore have the same problem? Yes, yes. Basically, this is intrinsic to the hardware. It is not like the fact that you so the Institute of Electrical Engineers that have basically implemented standards for basically all computers, whether it's your phone, your Mac or PC or whatever, all of them use 64-bit floating point numbers and they all have the same problem. And it's not going to be R only, it's going to be everything. Python, C, they all have these floating point number limitations. So it's intrinsic to the hardware. We have some workarounds. We have like long floating point numbers. So instead of 64 bits, we use 80 bits, and that affords you a little bit more decimal precision, but that's still not real numbers. Like, you get a few more decimal places of accuracy, and so it just kind of staves off the problem a little bit, but the problem still at its core exists. And the core problem is that real numbers have infinitely many decimal places of precision, and we can't do that, right? This is just like with real numbers, it's basically you're asking like, what is this? If I ask you, what is the smallest number that you can add to one that is going to make it distinct from one? Like with real numbers, you cannot answer that question. There's no way to write a value. Okay. But on the computer, we can answer that. That's machine epsilon. It's just going to be how many mantis bits you have, right? It's 2 to the negative 52 on the computer. With a 64-bit system, with a 80-bit system, it's, I don't know, 2 to the negative 60, 64 or something like that. But we have different we have a machine epsilon. We have this idea of like, this is the smallest thing you can add to one, whereas in real numbers, you cannot give me an answer. What is the smallest thing you can add to one that is going to be distinct from one? There's no, like, can't write that down, right? I don't know. I mean, the concept exists, but can you write it down and tell me what that number is? No, you can't. Okay. So anyway, to just kind of avoid this issue, and computationally, instead of basically I don't want to have something on the order of 10 to the negative 10 to the 14. And then when I invert this, I'm adding something because my machine epsilon is on the order of 10 to the negative 16. I've got around 16 decimal places of precision. So basically I'm just going to just scale it down. And instead of having 3 million, I'm going to just divide everything by 10,000. And I'm going to just have 359. Instead of 3,610,000, I'm going to just have 361. Okay. And then it's basically the exact same matrix. I just moved the decimal place over 4 places. And now I can invert this. Okay. I can have X transpose X inverse, X transpose T, and now the computer has no problem solving it. And now I have I get this, okay? 396.328, negative 0.382. And then just this thing, remember we scaled it down. Um, by a factor of kind of 10,000. So, the true term is, some a different order of this, but this is what we have. So we're able to solve this. I get my W hat, and if I say, hey, you know what, do LM on the same kind of adjusted, so not the original X values, but my kind of adjusted values where I scaled it, okay, we get the exact same results. Here, you can ask LM and R to make predictions using an X matrix. By default, it would want to add an intercept term, but because we have an intercept term already at that column of ones, we put in 0 plus. We say predict 0 plus, and this just means don't add an intercept term. Okay, and we get the same numbers, right? 396.328, negative 0.382, 0.944, 396.328, negative 0.382, and 0.944. Okay, so that's a good sign. And again, we're just kind of doing some workarounds to avoid some of the problems we run into with floating point numbers. So it's not, we haven't solved anything really. We just said, we haven't solved any intrinsic problems with floating point numbers. We're, we're just adjusting things so we're not running into that issue. Okay. So this is what we have. We can make our predictions by doing X times W hat. X times W hat gives me my predicted values. And this is what we have. And so this is going to now be my quadratic fit. And it looks like this. Okay. And yeah, that looks like a pretty good fit. Um, honestly, uh, when it comes to like fitting lines and it's like, okay, linear fit versus quadratic fit, I look at this and I go, yeah, that looks pretty good. If I go all the way back to just the linear fit, this also looks pretty good, right? Like which one's doing a better job? We say, hey, that looks decently well. This one also looks decently well. So, but this is our quadratic fit, and we can see the curvature that appears here. Okay. So, we can also, what if we want to do something like a third order polynomial, right? Like a cubic term or something like that. Um, we can do this, but we can add a third column. Um, but we start running into this issue of multicollinearity. Okay, all right, we have a question. It says, would you be checking the same model assumptions for the quadratic model? Yeah, so okay. There is a distinction between your classical linear regression and then like machine learning methods. So here I'm kind of taking a machine learning approach to linear regression. But yes, so in classical linear regression, we have a mathematical model that says, we're assuming our errors are normally distributed around our prediction line, right? And so therefore you're checking these assumptions of like, are my errors, do they have the constant variance throughout the whole thing? And when we do, and so yes, if you were doing linear regression and you're fitting a quadratic model in linear regression, you're still supposed to have all of these same kind of assumptions. You still have like this, your predicted value, and you're expecting your errors to be normally distributed around that. But when we do machine learning, we just we say, well, we don't really care about the math anymore. We just want good predictions. Um, and uh, there's a slight part of you that when you first start doing this, you feel a little bit like you're doing something illegal or something. And it feels a tiny bit um, uncomfortable. But yeah, with machine learning, we evaluate our performance strictly on predictions, our predictive ability, and we say, you know what? If it's making good predictions, it's got to be an okay model, even if like mathematically, you try to justify all these, we don't really have the same kind of assumptions mathematically regarding like the mathematical model and things like that. Um, okay, but going back to what I'm saying over here is that, when you have these um, terms and you just say like, okay, we have x and we have x squared and we have x cubed and we have x to the fourth and whatnot, you end up getting these highly correlated um, columns, right? Basically, as x gets bigger, x squared gets bigger. As x squared gets bigger, x cubed gets bigger. As x cubed gets bigger, x to the fourth gets bigger. And you end up getting, correlations like of, 0.99, 0.98, things like that. And you run into the same kind of issues of multicollinearity, right? Your parameter estimates start to become unstable because when you have things that are highly correlated, then it's difficult to know which one is the one that's actually important, right? So like if you look at a whole bunch of houses and you have things that are highly correlated is the square footage and the number of bedrooms, okay? And because these things are highly correlated, if you look at one data set, you might find the term that's significant is square footage and the number of bedrooms is not important. But then if you look at another random data set, just kind of by coincidence, you could end up having the significant term being the number of bedrooms and the square footage is less important, right? Because they're highly correlated and it's difficult to tell which one is which. And the same kind of issue exists here when you just take X and you square it and you cube it and things like that. And then you have this high collinearity problem and, which term is the important one? Is it the X squared term and the X cubed is not important? If you have another random data set, maybe X cubed is important and X squared is not important. Things like that could happen. And so, one thing that R is able to do is it is able to create, um, I guess, uncorrelated polynomial values. Let me see if I have a picture of this. I don't. Um, but basically, if you want to, okay, so if you have just, um, right, so if you have, let's see, if I have X and I have, X squared and X cubed and X to the fourth. You just have these highly correlated things. Okay. What R can do is it can create these, at least for the range that you are looking at. Okay. You can have the linear term, and then you can create an x squared term, which at least for this range of values, like from here over to from here to here, okay, the correlation between x and x squared is equal to 0. Okay. Obviously, if we expand on this even further, we might not get that. We can have an x cubed term, and it might look something like this. Okay. At least in this range of values from here to here, the correlation between x and x cubed is also 0, and then the correlation between x squared and x cubed is equal to 0. If I expand this further, right, and I have this going like that, um, and this continues on, and this continues on, then there's going to be correlation between x and x cubed. But at least within this window of points here, there's correlation 0. Okay. And that's what the poly function does is it's going to create, it's going to take your column of x values and, just creates, and it's hard to see what's going on here, but it creates uh, basically these different orders of magnitude, not magnitude, x and x squared and x to the third and x to the fourth and things like that. But it kind of moves them around so that you get things that are uncorrelated, at least for the range of values that you have. Whereas over here, x squared, x cubed, and x to the fourth are all highly correlated. Okay. And here they are uncorrelated. And this allows us to pick out, is there truly a relationship with the third order polynomial, or is there truly a relationship with the second order polynomial? Okay. So, um, so what did I write? I wrote, while scaling down big numbers works for polynomials of high degree, our values can become very highly correlated, which introduces other problems. And so one solution is to use R's poly function, which will scale the values and calculate uncorrelated polynomial values. Okay. And so here I've created just an X matrix using poly, second order X matrix, and this will have basically an intercept, a slope, and a X squared term. Okay. Now, one issue here is that because these values no longer kind of correspond to the original values, it's hard to really distinguish, understand what these terms mean. So, every time you do another kind of step of abstraction, you lose a little bit of that interpretability. Okay. But we can, the point when you use poly or something like that, you're not actually going to be using those coefficients directly. You're just trying to see are these terms significant? Okay. You can still kind of do fitted values. LM stores the fitted values, and we can do that, and we get our predictions. But I wrote an unfortunate side effect of using poly is that all of the x values get transformed, so the interpretability of coefficients is dramatically reduced. The coefficients for each term only make sense for those transformed values, which we don't really like. You can ask R, how did you transform these values? But it's not something that we generally work with directly, okay? But poly is still useful in that we can compare polynomial fits of different orders, and I can try fitting a whole bunch of models comparing the results, even if we lose the direct interpretability of the coefficients. So just for fun, I guess, I'm going to fit a third order polynomial model, a fourth order polynomial model, a fifth order, and a sixth order polynomial model. And that function poly makes it really easy because I can just say, hey, predict time using a third order polynomial, fourth order, fifth, and sixth order polynomial, rather than having to create that matrix, where I'm binding the column of ones, the column of x, the column of x squared, x cubed, x to the fourth, x to the fifth, x to the sixth. Okay. Because by the time I would do, take year and I say raise it to the sixth power, then we're going to get these really huge numbers. And then I have to do that scaling operation again. And so, it becomes a headache. We don't have to deal with that directly. We can just use some of these built-in functions in R, like poly. Okay. And then I'm going to take all of the fitted values. So I've got, my second order, third order, fourth order polynomial fit. I've got, poly 2, poly 3 model, and I just take the fitted values. I'm going to color them each with a different color, and I'm going to plot them. Okay. And this is what we have. So we have the linear in red, the quadratic in orange, the third order, fourth order, fifth, and sixth order in these different colors. We get kind of this braid of rainbow colors, and all of these things, like it looks kind of pretty, but then when you look at each individual line, you go, I'm not so sure if this is the right fit. Okay. And so the question is, which of these lines does the best job, right? Which of these lines does the best job? And this is a core problem in every statistical context. And so when you take 102A, no, 101A, your linear regression course, you learn a few different things and you say, well, all right, let's look at the summary of this thing, and we're going to look at which of these terms are significant, right? So you have the intercept, you have the linear term, the quadratic, the third order term, and so on and so forth. And we have stars on all of these things. And so we say, these all look significant. There's other tools that we can use. We have the AIC, what is that? The Akaike information criterion and the Bayesian information criterion. And basically these um, take a look at, your fitted values, but you have a penalty for how many additional terms, right? How many terms you have. It's like the log 2 penalty or whatever. And so, you balance these things out. You can also look at your adjusted R squared or your R squared values to try to to decide which of these things to use, right? So here's the summary table for the third order polynomial model. Here's the summary table for the sixth order polynomial model. And it looks like the first, second, and third terms are significant. And the fourth, fifth, and sixth, I don't know, the fifth one has a p-value of 0.07, but is that really the thing? And so, we have these different kinds of tools, and how we measure performance and choose which of these models we should use is a little bit there's a lot of questions, right? So, using only the R squared value, that's usually not recommended, because the R squared value, you can always eke out better R squared values by adding more terms, right? So the third order polynomial, my R squared is 0.8973, and here my R squared value is 0.9233 when I add additional things, and so in classical linear regression, you learn things like the likelihood ratio test or your F test, and you compare, was it worth using the additional degree of freedom for that additional term to estimate, and things like that. We look at the summary table. You have all of these things, okay? And we say, okay, well, the fourth and fifth and sixth order components aren't significant at the 5% level, whereas the linear, quadratic, and cubic components are significant. Does that mean we should just take the third order polynomial fit and just say we're done because this is the one that's best? And so what we want to do next week, okay, so our lecture is coming to a close here. What we want to do next week is we want to introduce how are we going to evaluate our model performance, okay? And so this is where we take a departure from classical methods. The classical methods, we look at, our statistical probability fit. So we say, what is the test statistic for this coefficient compared to its standard error, and is that significant, and things like that. And we're taking the departure from that, and we're going to just use cross-validation. We're going to just see how well does our model predict new values, okay? And so that is going to be the approach that we use in machine learning, is that we don't take this thing, we don't really care about statistical models anymore, and we just say, hey, can we make good predictions? And so that's what we will look at next week, is we look at how we use cross-validation or other kind of ways to measure our model performance by looking at its ability to make predictions. Okay. Oh, I forgot to give you your view quiz answers. I think I need to give you two more, right? So your second one is E, E as in elephant, and your third view quiz answer is B, B as in bear. Okay. E as in elephant is your second answer, and B as in bear is your third answer. Okay, we'll wrap things up here for today. Have a good weekend. Um, I'm feeling mostly better, so I'm hoping the plan is to be in person on Monday of next week. So I plan on showing up on campus and teaching. If things change, I'll send an announcement. I'll let you know. But that's the hope is to be back on campus next week. Okay, thanks everybody. Have a great weekend, and we will see you next week.